Hello dear students. Let's see this question that came in JEE Advanced Paper 2 Physics in the year 2019. The question is from the topic of radiation pressure and most of the students could easily solve this question in the exam. The question was fairly simple, procedural, but in my opinion, there was an assumption that we make without even realizing it while we solve this question. So let's see how to solve this question and what assumption I'm talking about. So first, let's look into the data of this question. So this is a mirror of mass m, which is connected to a spring of a spring constant k. Let us assume, which explicitly is not mentioned in the question. So light particles, photons, large number of photons strike the mirror, and the mirror is perfectly reflecting. So this, of course, mirror will gain velocity and it starts oscillating with angular frequency omega, such that 4 pi m omega by h is equals to 10 to the power 24. This has been given. H is the Planck's constant, m is the mass of the mirror, and omega is the angular frequency. The number of photons is capital N, and the wavelength of each photon is 8 pi into 10 to the power minus 6. Okay. This is, no, this was 10 to the power, this is wrong. This is 1 micrometer. This was 1 micrometer, not 14 meter. So IIT had given 1 micrometer. That means the amplitude of the oscillation was 1 micrometer. So basically, when the photons will strike this mirror, it will have a maximum compression of 1 micrometer. So basically, we have to find the value of n. If n is represented as x into 10 to the power 12, so we have to find this value x. Okay, the question is fairly simple. So since the mirror is perfectly reflecting, so what we can say that photons will strike with the momentum of h upon lambda, single photon I'm talking about, and it will reflect again with the momentum of h upon lambda, since the mirror is perfectly reflecting. So we can say that change in the momentum of a one photon is 2h by lambda. So what will be the change in the momentum of n photons? Because total number of photons striking is capital N. So we can say that 2h upon lambda into capital N is the total change in the momentum of capital N number of photons, right? This should be equals to momentum gained by the mirror. We can say that since all the photons are striking simultaneously, so we can assume that time of collision will be almost zero or super small. So we can apply principle of momentum conservation. Spring will not apply any force at that time. Okay, so we can say that momentum will remain conserved. Even if the spring would have been in the compressed state, then also we could have applied the momentum conservation, because if we assume time of collision to be very small, so 2h upon lambda into n, that should be equals to momentum or the velocity change in momentum of this mirror, which we can write as mv naught. Right now, if you realize this mirror will start moving towards right with velocity v naught, and rather it will start performing simple harmonic motion. So we can say that v naught is the maximum velocity of this mirror, because this is the velocity at the equilibrium position. Hence, we can write this as a omega, correct? A into omega, and maximum compression is 1 micrometer. So of course the amplitude must have been 10 to the power minus 6, which is 1 micrometer only, right? So m into a into omega. Omega is capital omega, which is angular frequency of the SHM given in the question. Now we can use this data. If you see carefully over here, so what are we getting? Lambda ka value has been given as this 8 pi into 10 to the power minus 6, so we can substitute that as well. 8 pi into 10 to the power minus 6 into capital N, that should be equals to m into 10 to the power minus 6 into omega. Now m omega by h you can bring this side, right? So I am bringing h this side, m omega by h 4 pi. So this 2 and this will become 4 pi, and 4 pi you can take this side. So basically n will become 10, this 10 to the power minus 6 also you can take this side, minus 12 into m omega into 4 pi upon h, right? So this was 10 to the power 24, and hence we can say n becomes 10 to the power 12, right? So basically this x is nothing but 1. X is nothing but 1, correct? This was the answer given by IIT. So this was the answer. But now, where have we taken an assumption? Interestingly, I told you that we are taking an assumption, but where did we take an assumption? Let's see. So if you think carefully, so if a photon strikes and it returns, so we are assuming that wavelength of the photon remains same. Now think carefully, if the wavelength of the photon remains exactly same, then that means we are saying that there is no change in the energy of the photon, right? That means all the photon go towards right with the same energy and they reflect with the same energy. Then from where did the mirror get energy? Mirror को energy कहाँ से मिली? So actually, in my opinion, when photon will reflect, there will be a slight, very small change in the moment wavelength of the photon. Its wavelength will increase very slightly. The change in the wavelength is so small that we have almost assumed it to be same. Now, why is the change in the wavelength very small? That we can actually see, when we will do the calculations, then we will be able to realize that that change in the wavelength is super small, and hence that assumption is very reasonable. So just for the understanding, or just for the clarity sake, let me show you. Let's assume that mass of the mirror is 1 kg. Just because in practical cases we can assume that mass of the mirror would have been 1 kg or 10 kg also, it doesn't matter. You will see that even if you assume this 10 kg or 100 kg, it doesn't matter. Unless and until if you assume that 10 to the power 10 or something like that, it would not make much difference. Okay. So practically speaking, if you assume this to be 1 kg, 10 kg, 100 kg, the change in the wavelength will be super small. Let's do the calculations. Let's take this data itself. Let's assume that number of photons striking are 10 to the power 12, and let us see if what is the change in the wavelength of the photon, right? It will be an interesting calculation. So what is the speed gained by the mirror? That is half m v square, and v ko we can write a square omega square. This is the energy achieved by the mirror. So this must have been at the cost of the photons, since the collision is elastic. So we can say that nhc by lambda, this was the initial energy of all the photons, minus nhc by lambda dash, this was the final energy, right? Now if you use the relation given in the question, 4 pi m omega by h is 10 to the power 24. So let me write this, 4 pi m omega upon h, right, is 10 to the power 24. Okay, so here anyway m is 1, so we can substitute this as 1 only. Okay, I've assumed just for the calculation purpose. A was 10 to the power minus 6, this will become 10 to the power minus 12. Omega ko we can put from here, so this will become h square 10 to the power 24 square, that means 10 to the power 48, right, divided by 4 pi square, that means 16 pi square. Okay, will be is equals to n into hc upon 1 by lambda minus 1 by lambda dash. Lambda dash is the wavelength of the photon which are returning or reflected photons. Okay, now value of n is 10 to the power 12. Value of h, you can cancel out 1h, and this speed of light is 3 into 10 to the power 8, and this is 1 upon lambda minus 1 upon lambda dash. And here what do we get? Here this will become 10 to the power 36 upon 32 pi square. Okay, now you just see the order of this value. So what are we getting? 12 and 8, this is 20, so this will become 10 to the power minus 16. No, one h was also there, right? So minus 6, not minus 16. Yeah, so h was also there, so this will become 20 16 and minus 34. So this means this is 16 and this is 10 to the power minus 34. I'm just writing the order, 6.63 divide by 32 pi square into 3, this is 1 by lambda minus 1 by lambda dash. Now you see the order of this value, like you can just ignore this, it will not create much difference. So if you see, this is 10 to the power minus how much, 18, 10 to the power minus 18 into some value, 6.63 divided by 3 into 32 pi square, which is not very significant. But this 10 to the power minus 18, so you can see this is super small, super small, and hence we can say that lambda dash must have been super close to lambda, because this is almost zero. You can see that, and hence we can say that lambda dash must have been almost close to lambda, and hence it was a very reasonable assumption to make, right? So this was all from my side. Thank you.